Hi, I'm here to present our work on deep multitask learning for joint localization, perception, and motion forecasting. Recently, we have seen a lot of progress on multiple problems related to self-driving, such as perception, motion forecasting, and motion planning. Many of these methods take as input high-definition maps, which can provide a rich prior for these tasks. However, leveraging maps requires precise knowledge of the vehicle pose, which is assumed to be error-free by modern approaches. Like any other system, localization systems can fail unexpectedly. The natural question is then, how robust are state-of-the-art self-driving stacks to localization error? We investigate this problem by simulating localization errors on two state-of-the-art perception prediction and motion planning modules. We benchmark failures on the LP3 dataset. LP3 is comprised of 1,858 sequences of 25 seconds each, recorded in a large North American city. This is a subset of the recently proposed ATG4D dataset that also has appearance maps available, which are necessary to benchmark localization, perception, prediction, and motion planning jointly. For perception and motion forecasting, we simulate a misalignment between the semantic map and the LiDAR reading. In terms of detection, mean average precision is fairly robust to translation error, but suffers a decrease of roughly 7% due to rotation error. In terms of motion forecasting, the mean distance between our predicted trajectories and the actual trajectories at 5 seconds increases by up to 30 centimeters for rotation error. For motion planning, we simulate a misalignment between the map and the output of the PNP module. We run the planner on the first frame and unroll the trajectory over 5 seconds. We observe a similar story. We see a much higher increase in collision rate at 5 seconds due to rotational error. Interestingly, the effect is less pronounced for the distance between the eco car trajectory and the trajectory chosen by a human driver. We now focus on designing a system that performs localization and perception prediction jointly. We designed the system with 3 goals in mind. First, it should have low latency and ensure its computational cost is small compared to the overall perception system. Second, we would like to leverage learning-based LiDAR localization to achieve robustness to dynamic objects and intensity miscalibration, while also reusing computation from the perception side. Third, we would like our system to be easier to train and deploy than its separate counterparts. The proposed architecture extends a state-of-the-art detection and multimodal motion forecasting network, the implicit latent variable model, with the ability to detect and correct pose errors with minimal computational cost. The pose estimation is done using a deep LiDAR matching approach over 3 degrees of freedom, x, y, and yaw, and the computed offset is then applied to the semantic HD map used in detection, forecasting, and planning. First, the perception system is trained by itself using ground truth object labels and pose information. Next, we freeze the weights of the perception system and train the localizer as a side module, leveraging feature maps from the perception LiDAR backbone. We benchmark our system on the LP3 dataset, focusing on motion planning metrics that measure both safety and comfort. First, we show the performance of a system with perfect localization, and how it degrades by introducing localization error just to the motion planning module, or the PNP and the motion planning modules. Although our system exhibits some amount of localization error, we see that we are able to match the performance of the sequential system on all the motion planning metrics. This is in line with our previous experiments, which show that PNP and motion planning are robust to small amounts of localization error. Moreover, because we share computation between localization and perception prediction, we can run the localization subsystem in as little as 2 milliseconds, providing an additional localization signal to the SDV.
We now showcase some qualitative results highlighting the impact of localization errors on motion planning. On the left, we see the autonomous vehicle planning its trajectory under localization error, causing it to plan an incorrect and unsafe trajectory. On the right, we see our proposed multitask system capable of detecting and correcting pose errors, producing correct and safe motion planning behavior. In this example, the pose misalignment causes the motion planner to think it is misaligned with the actual lane, and it performs an unnecessary correction which causes it to swerve dangerously into the adjacent lane. Once again, by detecting and correcting such pose errors, our multitask system is able to operate normally and safely. Thank you for your attention. Please refer to our paper for technical details as well as additional results.